This is the second of two lectures covering an overview of the seismic processing of reflection data. That is, processing of the data to produce seismic sections which represent a cross-section of the geologic structures in the Earth below the seismic line. Now, in the first of these lectures, we looked at the geometric processes which are used to correct for the geometry of the recording system that was used. And in this second lecture, we'll look at the signal enhancement processes which are used to remove some of the unwanted noise and reflections from the seismic data. So, just briefly repeating that then, the geometric corrections that we looked at are those which are necessary to correct for the geometry of the recording system. The fact that the sources and receivers are laid out in a certain arrangement, and applying those corrections to the data does give us a stacked seismic section on which the geologic structures are depicted as a reasonably true representation of the subsurface, although of course they're in a depiction of the travel times rather than the actual depths. However, the picture that will be obtained on a seismic section with just the geometric processes applied may not be very clear, because there are many other events on the seismic recordings than the primary reflections which we want to see. And so many of the other processes which are used on the data are for the purposes of signal enhancement. That is, they try to clarify the picture given by the seismic data by removing the unwanted events from the seismic section. Now, the processes which we'll look at in this lecture are the main ones which are used in virtually every processing sequence of seismic reflection data. And I'm showing here some of the names that are given to those particular processes in GSI's processing sequence, and just a brief indication of what some of them do. The first is a thing called true amplitude recovery, or TAR, and that applies correction for the amplitude losses which have occurred on the seismic data. That's often followed by a process called velocity filtering, or shortened to VELFILT, which removes certain of the non-random noise events, that is the surface noise modes, and also can reduce the random noise to a certain extent. Another process that's almost invariably used on seismic data is some form of deconvolution. A later version of that process is called designature, or DESIG for short. And the aim of these processes is to shorten and sharpen the reflection wavelets so that they give a clearer, better resolved picture of the primary reflections. If the multiple reflections are particularly strong, then a special process called demult may be used to remove or reduce them. Another process which almost invariably occurs in the sequence is common depth point stacking, and this is quite a powerful process for the reduction of all kinds of noise on the seismic data, and also reduction of the multiple reflections on that data. And often one of the last processes to be applied in the sequence to the seismic data is some form of frequency filtering, which reduces certain kinds of noise, mainly the random noise, which can remain on the seismic data. Well, the first process we'll look at in more detail then is amplitude recovery, or true amplitude recovery as it's often called. As the seismic trace is recorded at a receiver, it shows a very rapid decrease in amplitude with time due to various amplitude losses such as spreading losses, sometimes called spherical divergence, the absorption losses, and the transmission losses. So as it's recorded, it would appear something like this, with a very rapid decrease in amplitude. Now, the TAR corrections are applied to correct for those amplitude losses so that afterwards the trace would look something like this, with a reasonably even distribution of amplitudes down the seismic trace. The TAR correction actually consists of two components, one for the spreading loss, one to correct for that, and one to correct for the combined absorption and transmission losses. If we look at in fact, the logarithm of the gain or amplification that's applied to the traces against time, the correction for the spreading loss is a curve. The correction that's applied for the absorption and transmission losses is a straight line, although that's usually terminated at some particular time, T2 in the programs we use, and the gain is held constant after that. So the combined effect of these two corrections is, of course, an increase or relative increase in amplitude with time, which corrects for this situation and produces traces which should show reflections of similar amplitudes at the bottom of the trace to what we saw at the top of the trace. Now, sometimes the true amplitude recovery correction doesn't handle all the kinds of amplitude variations that we see on the seismic traces. So possibly either trace equalization or time variant scaling may be needed. If the traces show overall amplitude variations from trace to trace along the seismic line or across a record, we can apply trace equalization. This consists simply of measuring the average amplitude on each particular trace and then applying a multiplying factor or scalar to each trace to make the average amplitude of all traces the same. So we've removed the sort of overall or average amplitude variations from trace to trace. Now, situations also occur where the amplitude varies in time down the trace in some way which we want to correct. In a situation like that, we can apply time variant scaling. In this case, we divide the trace into a series of consecutive time ranges, usually called time gates, and we measure the average amplitude in each of those time gates, and then simply apply scalars, multiplying factors, in each of those time gates to make the average amplitude in each time gate the same. These processes of trace equalization or time variant scaling can be applied at almost any point during the processing sequence where we need to make some correction to the amplitudes of the traces. The next process is velocity filtering. This is used to reduce many of the non-random types of noise, and these are mainly noise modes which are generated by the seismic source. And the most common of them are these near-surface waves, some of which are illustrated on this diagrammatic record. This represents an off-end recording with source to receiver distance increasing in this direction and, of course, record time in this direction, so that the first arrivals P-wave arrivals by a direct travel path would lie along some straight line like this across the traces. Refraction and reflected refraction events often follow those first breaks roughly parallel to them, as is depicted here. And the slow velocity ground roll direct wave would lie roughly along a line like this at a much steeper dip across the seismic record. Now the reflection events, of course, this includes both the primary and the multiple reflections, lie along move-out curves across the record. Now if we look at the dips of these various events across the seismic record, we can draw them out in a little diagram, a dip diagram, showing the range of dips of each of those different events. And obviously the ground roll has the steepest dip. The first arrival energy and the refractions and reflected refractions all have about the same dip, maybe occupying a small range of dip somewhere here. And it normally turns out that the reflection signal dips occupy a range which is different than either of these two main kinds of noise, as depicted here. The signal, although it's curved, can be considered to be a series of different dips from an almost flat dip on the inside traces to a steeper dip across the outside traces. Hence it occupies a range of dips. Now, since the near-surface noise modes have a different dip across the seismic record than the reflection signal, it's possible to design a process which discriminates these different dips and can remove or reduce the various noise modes without affecting the reflection signal. And that process is called velocity filtering. The name velocity is used because horizontal velocity, or strictly speaking it should be apparent horizontal velocity of travel across the seismic record, is simply the inverse of the dip. Velocity would be distance divided by time, and dip would be time divided by distance. Well, the process of velocity filtering is illustrated on the next slide. We'll repeat again the diagram of the seismic record with the signal and different noise modes and the dips of those various things on the dip diagram. Now, velocity filtering is a process which operates on all of the traces of the seismic record at the same time. And in doing so, it can discriminate against the events with different dips. And the process is arranged so that events with very steep dips either in this direction, as the noise modes have, or in fact steep dips in the opposite direction, which can sometimes occur. All those events with dips in those ranges are rejected. A certain range of dips, which can be specified by the user of the process, is passed without having any effect on them. And that range of dips which is passed is chosen to include the range of signal dips. So the result of applying velocity filtering to this record is to remove events with these dips, which are the various noise modes, so that we'd obtain a record which now looks like this, showing just the various reflection events and possibly just a trace of some of the stronger dipping noise modes, such as the first arrivals. But by virtue of this velocity filtering process, then, we've removed or reduced to a large extent the near-surface noise modes, which are events that we don't really want to see on the seismic data. The next process is really a class of processes called deconvolution. There's quite a wide range of types of deconvolution. However, they all have really the same aim in common. If we imagine two reflectors, A and B, which are with a relatively small thickness between them, and the travel paths to those two reflectors, then if we recorded a seismic trace from this arrangement of source and receiver, we may see a trace something like this. Now, this would be because the reflection wavelet, that is the seismic energy wavelet that's reflected, is a relatively long wavelet in time. And since the reflectors A and B are together, fairly close together, the reflection wavelets for A and B overlap. And this overlap makes it difficult to distinguish on the seismic trace that there are in fact two reflectors there. In other words, the trace has a relatively low resolution from the point of view of distinguishing reflectors which are close together. Now, the purpose of deconvolution is to take a trace such as this, the way that it may look on an actual record, and to try to shorten and sharpen the reflection wavelets, so that after deconvolution the trace would look like this, where the two reflectors A and B are clearly distinguishable as two separate reflection wavelets. And that is because deconvolution has shortened the reflection wavelet to something much shorter. Now, the reflection wavelet, as was explained in an earlier lecture, actually varies in its length down the seismic trace. This is because as it's traveled a longer distance through the Earth to the deeper reflectors, and it always tends to increase in length with a greater distance that it's traveled. So in reality then, we have a situation where the seismic trace may look like this before deconvolution, where each reflection is in fact some wavelet which tends to increase in length with time on the trace. So that deconvolution really needs to be a process which distinguishes this changing wavelet length and tries to convert the reflection wavelet, no matter what its length is, to the same short, sharp reflection pulse. In fact, it can never quite achieve that. There's usually some slight lengthening of the reflection pulse after deconvolution, but generally all the reflection wavelets should be much shorter after deconvolution than they were before, so that hopefully we would obtain a trace like this, where there are now certain reflection events which are fairly clearly distinguished on the trace. Now, the various deconvolution processes that are used by GSI are listed on this slide, or at least the more common ones are. One of the older types of deconvolution was a process called time-variant deconvolution, or TVD, and that comprised two basic types, either whitening or spiking. That was alternative names for one of the two types. The other type was sometimes called predictive deconvolution, sometimes called gap deconvolution. The difference between those was that whitening or spiking deconvolution tried to convert the reflection wavelets to a single spike, a very sharp impulse. It could never quite achieve that, but in trying it would sometimes tend to build up a certain amount of random noise on the data. Predictive deconvolution is a process which doesn't try quite as hard to shorten the wavelet, but at the same time doesn't build up quite so much random noise. Those deconvolution types are both time variant. They both try to distinguish the time variance of the wavelet length on the trace and to shorten it to the same short reflection wavelet. They can both be used on data before or after the common depth point stacking process. Later deconvolution types, which are more commonly used now by GSI, are a process called designature, which is used before stack, and a process which really comprises three types of deconvolution. This is transcomp, transmission compensation deconvolution, which consists of types called gap, tcomp, and NMP. Now, designature is not a time-variant deconvolution. It just tries to determine the average wavelet shape on the record and shorten that somewhat before stack. And then transcomp, transmission compensation deconvolution, is a time-variant deconvolution process which does try to detect the remaining time variance of the reflection wavelet and do some further shortening of the wavelets, particularly on the deeper reflections. The reason for the change to these two deconvolutions is that it's possible by this combination to achieve a shorter wavelet eventually than by the older time variant deconvolution, which tried to do the whole process in one operation. The next process is multiple attenuation. And this is really a special adaptation of velocity filtering to be used for the attenuation of multiple reflections. Now, on the seismic record or in fact this would be a set of common depth point traces to which the process would be applied. The primary and multiple reflections all show normal move-out curvature across the set of common depth point traces, but generally the multiple reflections show more curvature, more normal move-out, than a primary reflection at about the same time. Therefore, it's possible to apply normal move-out correction to this common depth point set of traces, but this would be normal move-out correction which is for the multiple reflection curvature. So that after that NMO correction, the multiple events would be at the same time on each of the CDP traces, so they would be flat across the CDP traces. The primary reflection events would now curve the other way on the set of traces. Now, if we look at the dips of these different events on the NMO corrected data, the multiple event dip is now horizontal, zero dip, and the primary reflection curved events occupy a range of dips such as this. So we have a difference in dip of the primary and multiple energy, and we can use a velocity filter to attenuate the multiple energy without affecting the primary energy. And that's illustrated on this slide, where again we see the primary and multiple energy with their different dips. We can use velocity filtering to reject this range of dips, which is chosen so as to include the multiple dips, and pass all other dips outside that, which of course include the primary energy. So that after applying that process, we'd obtain a record like this, where there are only the primary reflections left. The multiple events have been attenuated, but of course we still have the multiple correction on this record for the multiple events. So the final step in the process is to reverse that normal move-out correction and put the primary events back to their right normal move-out curvature across the set of CDP traces. This process is not used all the time on all data, It would only be used where the multiple reflections are particularly strong. Now, perhaps one of the most important signal attenuation, signal enhancement processes in the sequence is common depth point stacking. As was pointed out in an earlier lecture, this is also part of the overall geometric corrections that is applied to the seismic data. However, common depth point stacking will attenuate many forms of noise on the seismic data. Common depth point stacking is, of course, applied to a set of common depth point traces, and after normal move-out correction, those traces would show the primary reflection at the same time on each trace, whereas other events such as refractions or first arrival events would still show some kind of dip, time difference across the traces. Multiple reflections would normally show a slight amount of curvature still, because the move-out correction was designed for the primary events, not for the multiples. And also, although I've drawn it separately here for clarity, there would also be a certain amount of random noise on the traces. Now, when those traces are summed together in the common depth point stacking process, we would tend to obtain a trace looking like this. Because the primary events are at the same time on each trace, we would be summing together similar amplitudes on each trace. So in general, with a summation of 6 traces such as this, the amplitude of the primary reflection would increase by a factor of 6. With an event such as the refraction events, we may have a situation like this where we would be summing a positive amplitude on one trace with a negative amplitude on another. So there tends to be some cancellation of these events in the stacking process. They wouldn't disappear completely. There'd be a slight amount of remaining energy from them on the stack trace. A similar situation occurs with the multiple events. We are in some cases summing positive and negative values together, so they tend to cancel out, and the multiple event would be reduced in amplitude compared to the primary. The random noise, because of its randomness, also tends to cancel out to some extent. You're sometimes summing positive and negative amplitudes. It would in fact increase in amplitude a little bit on the stack trace compared to the input traces, but it wouldn't increase as much as the amplitude of the primary reflection. Now, the stacked data is not usually left in this case showing higher amplitudes for the primary reflection. It's normally scaled, or sometimes it's called normalization, simply by dividing each amplitude by the number of traces that were summed together. So in this case, we'd divide all the amplitudes by 6, and this would be the final common depth point stack trace, so that it would show primary reflection with the same amplitude as on the individual CDP traces before stack, and all the other kinds of noise would be at lower amplitudes than on the input traces. So common depth point stacking is a signal enhancement process in that it distinguishes primary reflections from various other kinds of events and enhances the primary reflection data. Frequency filtering is often one of the last processes applied to the data before it's displayed in the form of seismic sections. And it's mainly used to get rid of some of the random noise which occurs on the traces. The deconvolution processes can tend to build up certain kinds of random noise on the data at the same time as they're shortening the reflection signal. The noise they build up is usually what is called high frequency noise, in that it would look like this relative to the reflection signal. High frequency simply means that the wiggles on the trace are more rapid than they are in the case of the signal. So in other words, the period or peak-to-peak distance, say, average peak-to-peak distance for the random noise would be shorter than it would for the signal. A shorter average period means a higher frequency than for the signal. So the process trace before filtering would maybe look something like this. It's a combination, or really just a summation of these two types of thing, the high frequency noise and the various reflection signals. Because of the frequency difference, we can design a filtering process which tends to eliminate the high frequency data while leaving the low frequency data, which consists mainly of the signal. So we can take this trace and apply a high frequency cutoff filter to get rid of the high frequencies and leave mainly just the frequency range which covers the reflection energy. So this is very often one of the last processes to be used before the final display of the stacked data. Well, these various processes are used in a certain sequence. They can't be used in any order. There has to be a certain logic to the order in which they're used. And the typical sequence is shown here. Amplitude recovery is generally the first thing to be applied because it puts the seismic traces into a form where if we display them at any stage during the processing, they have reasonably even amplitudes down the trace, and therefore we can see all the various reflection events. Velocity filtering is usually the next process because that removes various kinds of noise before we go into the deconvolution process, either designature or TVD. Deconvolution tries to determine the reflection wavelet shape on the data, and it can do a much better job of this if all the various noise events are reduced before the deconvolution. So if we try to get rid of the noise events before trying to determine the reflection wavelet shape. Now, all of these processes are applied to the data which is still in the same kind of records as it was recorded in the field, that is common source records, where all the traces on the record came from the one shot. The traces then at this stage would normally be regathered into common depth point traces because the following processes operate on sets of common depth point traces. Multiple attenuation, that is the demult process, would be used at this stage if the multiples were strong enough to need it. Then that would be followed by normal move-out correction of the primary events, of course, and static corrections if this were land data. Then at this stage, common depth point stacking would be done, of course, after the normal move-out and static corrections. And this is really one of the main dividing points in the processing sequence. All the processes before this must be applied to the individual traces before they're stacked together. Now, after common depth point stacking, the number of traces to be processed is reduced in the stacking process. So obviously there's some benefit to using processes after stack wherever that is possible. It's obviously going to be more economic since there are less traces to be processed. Deconvolution is often done after stack as well as before. We pointed out that if designature is done before stack, you generally do transmission compensation deconvolution afterwards. TVD may be done both before and afterwards. Main reason for that is that certain of the events such as reverberations may be better attenuated before the data is stacked, but after stacking the random noise has been reduced to the point where a better estimate of the reflection wavelet shape can be made, and so it can be shortened to a greater degree by deconvolution after stack. So hence there is some reason for doing deconvolution both before and after stack. Migration would be the next process to be applied if it's needed, and that might often be followed by bandpass filtering to get rid of some of the high frequency noise that's been produced by the deconvolution process. The order of these processes after stack is not quite so important as the order of the processes before stack. We could use these in different sequences without much difference on the final section. Well, the processes that we've looked at then in this lecture and the preceding one are the major processes which are used to convert the recorded seismic traces into a seismic section which gives a pictorial representation of the geologic structures below the seismic line. And we've used signal enhancement processes to try and make that picture as clear as possible. Now, there are many other special processes that might be used on the seismic data. We've only looked at the major ones. Perhaps two of the most important processes that haven't been covered in this lecture series, but will be in subsequent ones, are the analysis programs that are used to determine the velocities of travel of the seismic waves to the various reflectors, and processes to determine the static corrections which are needed for the seismic data. The velocity analysis, we've shown how velocity can be determined from travel times and offsets on the cone depth point data. And those velocities are then used in the move-out correction of the data before stack, or in the move-out correction that is needed in the demultiple process. The static corrections, of course, are needed before the cone depth point stacking is done. So this then completes the overview of the major processes that are used in a typical processing sequence on seismic reflection data.